So here we go, a plan. In no particular order. I'd like to share with you an outline for the lectures to come next week. And then today, I'm going to spend most of my time convincing you that boundary conformal field theory and defect conformal field theory are worthwhile studying, that they're interesting. And I'll use these acronyms as we go forward. So the B there is for boundary, and the D is for defect. And I was listening to a little bit of Professor Bova's lectures over the last week, and I know you've already seen a little bit of CFT stuff, conformal field theory. So I'm going to assume that you know a little bit going forward. And part of my challenge here is really trying to get the level right. I'm not exactly sure who I'm talking to, especially since I'm several hundred miles away. So I also encourage you to, if you're going to make comments, to try to help me get the level right by engaging me in some kind of conversation. And then I can adjust as we go forward. Anyway, the third thing I'd like to talk about is it's a sort of an aside about dimensional analysis. And in some sense, I think it's maybe the most important thing I'll say in my time here. It's something I feel like wasn't really emphasized enough to me, or maybe it was emphasized and I just didn't appreciate it as a PhD student. It's really something I've only really come to grips with as I've matured as a physicist, as a postdoc, and later on. So let me try to tell you a little bit earlier so that you can learn a little bit faster than I did. So that's my plan for today. And as I said, I'm lying a little bit about the order already with this plan to keep you on your toes. And I'm going to start actually with number 2. How can I start with an outline before I tell you why you should be listening to me? All right, so, and I also want to make sure I'm seeing the chat here in case anyone wants to write in. But of course, as Nopal said, please just unmute and launch in and ask me a question. It's maybe the most efficient way. So I want to start with number 2, which is why study conformal field theories, conformal symmetry, and why add boundaries and defects to them? So to address that, let's start by just talking more generally about symmetry and quantum field theory. And I think probably at this point you've been introduced to all kinds of different symmetries. Symmetry is clearly a very major topic in your education thus far. And we've come into contact with all sorts of different symmetries. And at first glance, this just seems like another one of them. Why is this one special? Why should we pay attention to this one more than, say, gauge symmetry or flavor symmetry or R symmetry? So indeed, gauge symmetry, that's something I'm sure you've seen a lot about. For example, the SU3 cross SU2 cross U1 of the standard model. It's a nice example. There are global symmetries. So by gauge symmetry, I mean some sort of local symmetry, something that you can act on locally on the field theory. So it can be somehow a function of position. Some people say that gauge symmetries aren't really symmetries at all. They're just redundancies in our description of the theory. So maybe that's a more modern perspective. We have global symmetries. Here's an example of a global symmetry. We have the SU2 flavor symmetry of the up and down quarks. It's approximate because the up and down quarks actually have slightly different mass. So you can't quite rotate them into each other, but in the limit that you treat them as massless, it's quite a useful symmetry to get some appreciation for the physics of the strong force and how mesons come from bound states of quarks and so forth. What else is there? There are discrete symmetries. So maybe examples of those are charge, parity, and time reversal. Those are important examples of discrete symmetry. And so why should we pay attention to conformal symmetry more than any of these other ones? Well, it's related to, I think, a symmetry you'll agree that is very special. It's related to the space-time symmetry group of special relativity. This is the so-called Poincaré group. This combination of translations and rotations and boosts. I emphasize the Poincaré group among all of these other symmetries I've been talking about because it in some sense gave birth to the subject that we've been talking about all week, this notion of quantum field theory, of relativistic quantum field theory. That you can think of relativistic quantum field theory as some kind of marriage of special relativity and quantum mechanics. So the Poincaré group, I feel, really has a very special place for us high energy physicists among all these other symmetries. And because of that, conformal symmetry plays a very special role in a way I'll now explain. So because of this sort of centralness of Poincaré, you're kind of led to ask, well, when can Poincaré be part of something bigger? Is there some way in which we can think of embedding the Poincaré group in a non-trivial way to some larger group? And since Poincaré is so important, maybe through its embedding, we'll see the importance of these other groups as well. And it turns out the answer to this question is that there's a very limited set of circumstances in which you can embed Poincaré in this way. And that's due to a theorem that was proved many, many years ago by Coleman and Mandula, proven in, I think, 1967. And the claim is the following, that if one takes an element, say G, in the Poincaré group, and one takes an element H of some other internal symmetry group, maybe it's the SU3 color symmetry of the standard model. The claim is that those group elements commute, that it doesn't matter which order you act with them on some state or quantum field, they combine in a trivial way. And so the only way it seems, if you believe the Coleman-Mandula theorem, to incorporate Poincaré in some larger context is in this purely trivial way. You just take direct products of additional internal symmetry groups. That Poincaré then seems even more special from this perspective, that you can't extend it. Now, of course, there are loopholes. With any proof, there are loopholes. There are assumptions that go into the proof of Coleman-Mandula. And it turns out pretty much all of these loopholes are extremely important. And the first one on my list, because of the subject of these lectures, is conformal symmetry. Now, how did that happen? How did conformal symmetry wind up being a loophole in the Coleman-Mandula theorem? Well, it turns out if you look at the proof in detail, the proof involves looking at the S matrix, or scattering matrix for particles in the theory. And if you try to define an S matrix for massless particles, you run into some trouble with infrared divergences. It's hard to really get to long distance if you have massless particles. So with massless particles, the S matrix, let's just say it's problematic. There are ways of defining an S matrix for massless particles, but that definition is not part of the Coleman-Mandula theorem. And then it turns out that if you try to extend Poincaré for a theory that just involves massless particles, what you end up with is conformal symmetry group, as we'll see in later lectures. So conformal symmetry, it provides this interesting loophole to the Coleman-Mandula theorem. And because it does, it suggests that because Poincare is so important, and this is one of the few ways we can extend it, we should take this symmetry group very seriously. There are other loopholes. One which you've been thinking about all week with Professor Bobev is supersymmetry. And here the loophole is a little bit different. So the proof of Coleman-Mandula requires a Lie algebra. The statement of Coleman-Mandula is more specifically about continuous groups like SU3, SU2, and so forth. And for those continuous groups, there's an underlying Lie algebra, as you probably studied. And supersymmetry does not involve a Lie algebra. SUSY involves instead a Lie superalgebra. Something where you take not just commutators of the symmetry generators, but anti-commutators, which is very natural because they're fermions, and you naturally want to look at anti-commutators of fermionic quantities. That's another extremely important loophole. And as you've seen this last week, supersymmetry is an incredibly interesting, very deep topic. There are other loopholes I'll just point out for the sake of completeness. So discrete symmetries don't work because, well, again, they're not continuous symmetry groups. And another interesting loophole is for spontaneously broken symmetries. So if you have some theory, you have some action which appears to have a symmetry, and then you look at the ground states, but the ground states don't respect that symmetry. So the ground state, we say, will spontaneously break the symmetry. In that context, you can augment Poincare by these spontaneously broken symmetry groups. But these we won't talk about at all today. We're not going to talk about discrete symmetries or spontaneous symmetry break symmetries, and supersymmetry you've already heard lots and lots and lots about, so we won't say anything about that at all. And so our emphasis is going to be on the conformal case. Okay, could it just be academic curiosity that conformal symmetry ends up as one of these few loopholes of the Coleman-Mandula theorem? Or are there areas for real applications? I think you've already seen a lot of these applications in the lectures this week. I was listening to Professor Bobev today, and he was talking about the bootstrap and conformal field theory. He was talking about the spectrum representations of the conformal algebra. So there's this nice intersection of theories which are both supersymmetric and conformal, where you can use both tools together to really get a very deep understanding of what's going on with these super conformal field theories. Putting both of these techniques together is really a very powerful way to make progress in theoretical physics. But let me point out some other interesting applications for CFT, which you may or may not be aware of or haven't thought deeply about in this context. I mean, I'm going through this because I felt like, as a graduate student, so often I would go to these classes and people would just dive in immediately to the details, the representation theory of some algebra. And I have no idea why I'm supposed to be interested in it, other than that someone I respected was up there telling me about it. And there's a little bit too much of that, I think, in our field. We need to really understand ourselves and internalize ourselves why we want to learn something, not just because I tell you it's interesting. Anyway, I'll get off my high horse on that subject. So applications for conformal field theory. So maybe number one on the list, because it's experimental, and so often a lot of what we do seems very divorced from experiment these days, is it's related to critical phenomena. What do I mean by critical phenomena? I mean materials that undergo phase transitions. There's this notion of a second order phase transition. So you're doubtless been aware of first order phase transitions since you were very young. Water freezing or water boiling, these are nice examples of first order phase transitions. They're a little bit discontinuous, and so there's often some discontinuity in the as you tune the temperature of the system. Second order transitions are a bit smoother. There's not discontinuity, but there's like a discontinuity in a derivative. And because they're a bit smoother, you don't have this phase separation that you would in first order phase transitions. You can treat the whole system as a single entity. And at that critical temperature, at the temperature where you see this phase transition, there's often an effective field theory description of the system. For example, the Icing model that Professor Bobev was talking about this week. So, in water boils, that's a first order phase transition, but if you tune the pressure, there's a critical line which ends at some point. There's a critical line in, let's see, how does this work? So if I'm gonna get this wrong, but because I didn't prepare it, but we can think about some temperature versus pressure for water. And there's some line, let's see, I'm not sure which way things are supposed to go, but maybe something like this, where that's gas and that's liquid. Yeah, I'm sure I'm not getting this right. But there's an endpoint to that line where the first order phase transition stops and becomes second order. So let me cross this out before it goes in the permanent record, although I know there's already been recording of my mistake there. So there's some effective field theory description which is second order, and that description, it's not just any field theory, it's a conformal field theory. At that critical temperature, you tend to get fluctuations at all scale as the material goes back and forth between its low temperature state and high temperature state. And because there's that sort of scale invariance of fluctuations at all scale, there's scale invariance, the theory has a scaling symmetry, which we'll see as an important generator of the conformal group. Let's put a little bit more meat on this and talk about a particular example, the Icing model. This is a lattice model, say a square lattice, and on each lattice site, we've got these spins, which take two possible values. Sigma I is plus or minus 1. There's a nice Hamiltonian, which has a coupling J between nearest neighbors. That's what this funny sum on ij with brackets means. It's just the nearest neighbor sum, sigma I, sigma j. And as you've probably seen, there's going to be a high T phase where there are lots of fluctuations, and the order is destroyed. And so the expectation value of all those spin variables is 0. And there'll be a low T phase where the system orders. It's favorable for the system to order if this quantity J is positive. And so you get an order parameter, which is like the expectation value of these spin fields. And between these two, at some critical temperature, at T equals Tc, there's a second order phase transition. It's believed to be in the same universality class of this, the critical point you find in for water in this between liquid and gas, where the liquid and gas phase transition ends, where you have the scale invariance and you have an effective conformal field theory description at the critical point. So that's a very useful experimental reason to care about conformal field theories. So another more theoretical reason to think about this, and you saw a lot of this, I think, in Professor Bobev's lectures that he was talking about through a normalization group and how you get CFTs at fixed points. So the rules we know in QFT depend on the energy scale. And maybe the most famous example of this is QCD, theory of quarks and gluons, or at least it's a theory of quarks and gluons at high energy in the UV. And it's actually just a free theory that the quarks and gluons become very weakly interacting at high energy. And we flow down in the RG to some low energy theory where we find bound states mesons and baryons, pions, protons, neutrons, so on and so forth. This would be the low energy state. And this is what we call a gapped theory or a trivial theory. Everything has mass. And if you go to a low enough energy where you can't produce any of those massive particles, there's nothing there. It's just an empty theory. But they're both examples of conformal field theories. The empty theory is a conformal field theory, and the free theories are also nice examples of conformal field theories. And that's a statement that we believe is more generally true, that the generic fixed points of relativistic QFT are conformal field theories. In this case, free and trivial, but generically, we also expect that we could have, if there are massless particles lying around, that they could be interacting as well. So the generic fixed points of a QFT, we believe, are conformal field theories, and they don't have to be just free or trivial. They could also involve interacting massless particles, and that's the subject of these lectures. And it's more than that, right? You have these nice fixed points where you have an enhanced symmetry group, and they become natural starting points for analyzing the behavior of the QFT more generally. As you saw in the lectures this week with Professor Bobev, and I think probably you've also seen extensively in your QFT classes, although maybe you haven't put it in quite this language. The last example I wanted to talk about was why you might care about conformal field theories is string theory. So quantum field theory we can think of as roughly a theory of point-like objects, at least in its traditional formulations. I guess more and more these days people are caring about extended objects in QFT, and these lectures are part of that story. But traditionally, it's a theory of electrons and neutrinos and so forth. And these are all sort of point-like objects that travel around. And as a result, they tend to be quite singular. Even the self-energy of a point-like charged object is infinite. It's quite infinite. And these singularities plague quantum field theory and make it very hard to deal with, as doubtless you've seen in a quantum field theory course. We have to add, some kind of counter terms in our action to subtract the infinities. We have this whole procedure of renormalization group, and you're probably well within your rights to say this is not the greatest procedure. It doesn't seem very well mathematically justified. Can we replace it with some structure that has better convergence behavior, less infinities, fewer singularities? And that's one way people have often motivated string theory. You can replace the points with higher dimensional objects. For example, strings, or they could be higher dimensional, higher than strings, although I guess the reason people typically don't go higher than strings is that it mathematically gets even more complicated to write consistent theories. But strings work very well. And part of the reason for that is actually a connection to conformal field theory. So for example, strings. And when you introduce these extended objects with higher codimension, the self-energy of them is less singular. The fields diverge less strongly as you go to the origin. You can get rid of a lot of these divergences that plague the original formulation of QFT. And that's part of what makes string theory so attractive. So what is a string, right? some object which has an extension in space, and it's going to move in time. And so as it moves in time and it has an extension in space, it traces out a 1+1 dimensional world sheet. And you go through the details, you take a string theory course, you learn that there is a two-dimensional conformal field theory living on the world sheet. And so a lot of the techniques that people have developed for conformal field theory then become very useful for understanding string theory, at least in 2 dimensions, and in fact in higher dimensions too, with the advent of more sophisticated developments like Adscft correspondence. Okay, so that's my spiel about why we should care about conformal field theory. And of course, this is not just a series of lectures about conformal field theory. This is a series of lectures about boundary and defect conformal field theory. So that's what I'd like to talk about a little bit next, why we should care about boundary and defect conformal field theory. But maybe this is a natural place to ask for questions and make sure that my writing is clear and people hear me and so forth.
Hi, can you hear me?
Yes.
Yeah, in the renormalization group, when you write the gapped, so what does it actually mean by gapped?
Gapped means massive. It means that the lowest energy states, or the effective fields that describe the degrees of freedom, they all have a mass. So in the case of QCD, the quarks and gluons, they form bound states, which you know under names like mesons and protons and neutrons. And all of those objects, every single one of them has a mass. The lightest weight one is a pion. And so if you're at energy scales below the mass of the pion, you're in the gap. You can't produce anything. And so the theory has nothing but maybe the identity operator.
Okay. I mean, in general, when we say a gapped system in condensed matter perspective, so does it mean that, does it any related to this context?
Yes. Yes, in condensed matter, it means something very similar. Of course, you won't have necessarily Poincare symmetry or some relativistic symmetry group, but you will have a notion of mass. And you can talk about the energies of all the states or degrees of freedom in the system. And if there's a gap, as long as you're not providing energy larger than the gap, you're not exciting anything. So people often talk about like a gap in the Fermi surface, right? Where if you provide not enough energy, the electrons can't tunnel to the higher band and start moving around.
Okay, thanks.
Other questions? Good question. I'm really happy to take questions. And again, that's the virtue of this kind of presentation, is that there can be some kind of interaction. And any way you'd like to ask, I'm happy to stop and discuss. This is supposed to be a very fluffy lecture, so maybe I'm not saying enough that's provocative yet, but let's go on. If there's nothing else. I have to say something provocative, like all quantum field theories come from the 2,0 theory. I think that's a great statement, by the way, Nikolai, and I'm really glad that you made it if you happen to be listening. It's a very nice conjecture, crisp, clean, worth working on. Anyway, boundaries and defects. Why should we care about them? And what do I mean by them anyway? So in the context of these lectures, I'm nearly always going to, well, that's a lie, but one context in which I'm going to discuss them is a sort of planar boundary. So I can only draw a few cases because I can only picture 3 dimensions in my head, although we'll be in arbitrary dimensions in general. But you can imagine some p-dimensional plane. It could be an actual plane, in which case it'd be, say, 2 dimensions. And it's going to have a normal direction or codimension. In this case, the way I've drawn it, there's just one normal direction. Q equals 1. Or I could imagine another case where I have like a p-dimensional line, which is also really a p-dimensional plane. But again, I can only draw 1 dimension here in 3 dimensions. And here I would have a way of going around the defect. So in this case, I would have, say, Q equals 2. And so my notation in these lectures is going to be that P plus Q equals D. We're going to have a dimension of the defect, codimension, which is the normal directions to the defect, and they're going to sum up to be the space-time dimension. And a lot of the time, I'm going to be talking just about flat defects, although at some point we'll let things curve around and exist in curved space, but that will come later. So this is my dimension, defect dimension, and the codimension. And the idea here is roughly to break some, but not all, of the conformal symmetry group. These things are very delicate, and it's very easy to set up situations where the boundary conditions just destroy everything. But I'm going to be interested in cases where I set things up with the right kind of boundary conditions or the right degrees of freedom on the defect so that I preserve some subgroup of the conformal symmetry group. And it's going to be enough to be very interesting to give us a little bit more constraint on the quantum field theory than in the absence of conformal symmetry, but less than in the case of a full conformal field theory. So why might we care about these kinds of objects in quantum field theory? Well, there's one obvious use, which is it's very clearly important for critical systems. It's critical phenomena I was emphasizing a few minutes ago. These systems, they're not infinite in extent. And so if you set up some system at a critical temperature, it will have a boundary, and it would be nice to understand how that boundary will affect the physics. So that's one very clear use. And also these materials that you study phase transitions for, they often have imperfections. You grow some crystal in some deposition chamber, I don't know what, but it's not always going to be a perfect crystal. There'll be dislocations and other kinds of imperfections in the crystal structure, and you can treat these as defects sometimes. And so again, it's very important to understand how these imperfections affect the physics in critical systems. Although in fact, I think there hasn't been all that much in the way of experimental work on precisely this. It's a little bit hard to find in the literature. I think often what happens is that the physics is dominated by the volume of the system. And so they wind up being rather small effects, these surface effects or defect effects, and you have to look carefully for them. So that's one obvious way of motivating the importance of these systems. But I have, at least from my perspective, a slightly more compelling one. I grew up as a string theorist, high energy theorist, and that's where most of my interest lies. And looking back, developments.
Hi.
Yeah.
Just to clarify, because in a p-dimensional plane, you are just have a normal direction, just a one normal direction. But why do you call it defect?
So, sorry.
Why q equal to 1? You call it defect dimension.
Oh, I'm being sloppy in my nomenclature, but I think what I'm probably going to wind up doing, so I don't always have to say defect and boundary, is that when I mean both, I'll just say defect. And the q equals 1 case, in particular, you can think about this maybe as a boundary if it's got no other side, or you could think about it as an interface if it's got another side. So the interface case might be, you could think of more as a defect. Although by abuse of notation, so I don't have to keep saying boundaries and defects in this lecture context, I'll probably often just say defect. Is that clear?
Okay.
But thank you for the clarification. Yeah, so they're clearly important for critical systems, but I have a more compelling argument for it, at least from my perspective as a sort of high energy theorist, string theorist, I think there's a way of reading the history of our field over the last 30, 40 years through defects and boundaries. As seeing many of the most major developments in our field is somehow emerging from the physics of these kinds of objects. And so I think it's then very natural maybe to take a step back and say, I don't want to just wander around the physics landscape at random looking for the next revolution. Since all of these major developments have somehow centered around defects, maybe I should focus my attention there. But why am I saying this? Well, D-branes. Let's think about D-branes. So these are surfaces on which open strings end. I think Nikolai drew some pictures of these last hour and was telling you how these are gauge bosons in some low energy limit. But yeah, more generally, D-branes are just boundary conditions for open strings. And I told you earlier that, what did I tell you? That there's a 2D CFT on the world sheet. So I'm just drawing here a spatial picture of the string. It's also moving through time, in which case it'll trace out this 1+1 dimensional world sheet. And the D-branes here are boundary conditions on that 2D CFT. Okay, so it's very clear there that there's an application for boundaries in conformal field theory. But I should also emphasize that D-branes were hugely important in the development of string theory. I think it's fair to say that they seeded the second superstring revolution. They gave us non-perturbative insight into string theories. They gave us evidence for string theory dualities. And they helped convince us that there weren't 5 string theories, that there's just really one, and we could take various limits of it and get the 5 that we had understood before. And to understand these dualities, it was very useful to have D-branes. They would provide some evidence that these dualities were really true. So D-branes is one truly major development, and I mean, they are defects in boundaries. They're boundaries for the world sheet living on the string, and they're defects also in the ambient space-time. Another huge development in our field over the last 20, 30 years is the Adscft correspondence. What is this? I don't know if there are lectures on this specifically at this workshop. It's a hugely important subject, and you should definitely study it. Adscft, it's a map between gravity and field theory. It's a statement that this maximally supersymmetric n equals 4 Yang-Mills theory that I think came up in the lectures this week in Nikolai's lectures, it's dual or equivalent to a theory of type 2b strings on a certain curved background, anti-de Sitter space across a sphere. But it's very interesting, right? Because it's mapping a field theory to a gravity, and it works in a very interesting way that, in the strong coupling limit on the field theory side, you get access to classical gravity on the gravitational side. So by studying classical gravity, you get to learn about strong interactions in field theory. And then in the free field limit, it maps to a kind of quantum limit on the gravity side. So by studying free fields in Adscft, you should maybe gain some insight into a quantum gravity. And these are two, I would say, of the most important problems in our field today. And that's why there was so much excitement about Adscft. The theory of quantum gravity and the problem of strong interactions in field theory. Confinement in Qcd is a famous example of that. So Adscft, I think, got everyone very excited because it promised so much by way of addressing these two fundamental questions in our field. And how is it related to boundaries and defects? Well, there's a CFT in the name, clearly. There's a conformal field theory here. And the CFT lives on the boundary of this anti-de Sitter space. And in fact, if you forget about the effect of gravity, there's sort of a quantum field theory way of thinking about ADS-CFT, which maybe we'll talk about a little bit later in the lectures, of thinking about boundary conformal field theory as quantum fields on anti-de Sitter space. But anyway, you see here there's a major role here of a boundary in this context, the boundary playing some huge role in the development of this central idea. All right, I've got a couple more examples. There's been a lot of excitement over the last, I guess, 5, 10, 15 years about quantum information and this notion also of quantum entanglement. I think from the quantum mechanics point of view, you can see entanglement, quantum entanglement. This is like the entanglement in the Einstein-Rosen-Podolsky experiment, where you have some decaying particle which produces two particles with equal and opposite spin. So you don't know, which particle has spin up, which one has spin down. But if you measure one as spin up, the other one immediately has spin down. They were entangled, right? But you can think of this entanglement also as a resource. This is the jargon they use to build a quantum computer. So if you understand these issues of quantum entanglement and quantum information well enough, maybe it will help from a theoretical point of view of developing algorithms and methods for building quantum computers. And on our side of the fence, there's this notion of, what is it, it from bit or qubit that I think John Wheeler was first espousing, that you could maybe somehow understand space-time itself as emerging from information. And I think this was first, I think people maybe first got very excited about this in the context of black holes, which seem to be not only geometric objects, but also objects that carry information and should have some kind of quantum realization. So by thinking about the seeming paradoxes involved with black hole evaporation, it's this sort of natural evolution to thinking about, well, maybe we can think about all of space-time as somehow having some information theoretic basis. So how am I going to connect this to boundaries and defects in conformal field theory? I'll just note that in a quantum field theory context, if you're going to compute entanglement or quantum entanglement, a very natural setup to use is you have your space and you divide it into two spatial regions. We'll call it A and B. And you can think about computing the entanglement between those two regions. And to do that, there's a technique which involves inserting what's known as a twist defect. It has codimension 2. Since these are spatial regions, they don't persist in time. And by understanding the physics of these twist defects, by being able to say compute a partition function in the presence of a twist defect, you can compute also the entanglement entropy. So there's this, again, close connection between boundary and defect stuff I'd like to talk about here and quantum information, which is, again, a huge development in our field over the last 10, 20 years. Okay, my last example is a bit outside my expertise, and it's maybe not as conformal in its nature, but I feel like it's also important enough that I should say something about it. We can say something about topological insulators. So these are materials. Some slab of a particular alloy or metal, or I don't know what, and they are insulating in the bulk. They don't carry charge in the bulk, but they have conducting surface states. If you look at the distribution of electrons in the Fermi surface, there's a gap in the bulk. So if you don't provide enough energy for electrons to jump over that gap, they can't then conduct electricity. But on the surface, there are these allowed states that cross the gap. And it is possible for the electrons to conduct electricity, but just on the surface. And you could ask, are these massless states on the surface, aren't they sensitive to, I don't know, various perturbations that may make the surface a bit bumpy or introduce some interactions or so forth? And the claim is that they're protected. They have protected surface states, protected massless surface states. They're protected by symmetries, usually discrete symmetries. And these have been very important in the condensed matter community. They actually have physical examples of these compounds. You can go and look at their electron spectra and measure the conductivities in various ways and see that they have the properties they should. So they're experimentally realizable. There's less of a direct connection here to conformal symmetry, but I would point out, I saw in a recent paper from a group at Harvard, they're saying that even though usually the topological insulators are insulating in the bulk, there's been some recent investigation into compounds which might also be gapless in the bulk, but have similar topological properties. And so again, I think there's some interesting connections here to condensed matter. Okay, so that's my list, and I hope I've gotten you not only interested, but potentially excited about this subject about conformal defects and boundaries. And again, I think this is a nice place to pause for questions. My plan in the following, I'll tell you a little bit about the outline of the lectures going forward, and I also have to tell you about dimensional analysis.
Hi, I have one question.
Yes, please.
That in your first example, the d-branes are, we can consider d-brane as a non-perturbative examples of space-time defect.
The d-branes is a non-perturbative example of the space-time defect.
Is it?
So I can say a little bit more about the d-brane case and how it relates to what we'll be talking about here. So maybe I can just say a little bit more clearly what I was trying to say before. So you can think about the conformal field theory living on the strings, in which case the d-branes are boundary conditions for this 2D CFT. So that's a very clear connection to what I'll be talking about going forward. But there's a slightly less clear connection. If you think about the target space picture for string theory, so these are strings propagating in some 10-dimensional space, and these are d-branes which exist in 3 or 4 or 5 or so forth dimension. And from that point of view, now it's a gravitational theory. So it's no longer a conformal field theory. And another key difference between that point of view and what I'll be talking about later is that you can think about the d-branes as being dynamical in this context, that they'll be kind of moving around this 10-dimensional or 11-dimensional space-time. Whereas the defects and boundaries I'll be talking about going forward, they'll just be frozen. I'm just going to have some defect or boundary that's frozen at a particular location. There'll be no gravity. There'll be no way for the system to back react on the location of the d-branes.
Yes, and then my question was, is there any perturbative example of defects, or defects always non-perturbative?
Oh, there are lots of nice examples of defects, especially with free theories that we'll get to as we go forward. Where you can completely understand what's going on. In understanding them with interactions is typically much more challenging, although I hope to present a few examples by the end. Any other questions? I mean, that was a question about my outline, which is what I'm going to get to next. So if there are other questions about what we'll be talking about, maybe hold off for a few minutes. But any questions about? Yeah, go ahead.
I just wanted to ask, when you say codimension, is that codimension of space or of space-time? Does that include the time?
It will always include time. And whether I'm in Lorentzian or Euclidean, you're going to have to keep on your toes, because I'll probably go back and forth a little bit. But I think at the beginning, I'll pretty much always be in Lorentzian, so there'll be a time coordinate, and that Q will include time. So this is a little bit different from the D-brane naming convention, where if I say a DP brane, that only includes the spatial directions. So a D3 brane would actually be a P = 4 defect in my lexicon. Anything else? All right, let's keep going. I'd like to give an outline of what I'm going to be talking about for the next few weeks. So at the end of this outline, I'm going to go back to this dimensional analysis mini lecture I've kept emphasizing, and that will be the end for today. But in the meantime, or sorry, afterwards, I have, I think, 7 more chapters in my notes. So I have some notes I've been writing up. I've written, I think, 7 of the 8 chapters total, and I'll try to make them available soon. Maybe I can even, let's see, I might even be able to, I wonder, I can even share them. No, I can't share them on Zoom, but I will post them on my website and also send them to the organizers, so they can probably be posted on the LACES website later today. They're not done yet. They'll be a work in progress, and they'll continue to evolve as the week goes on, but I'll make those available soon. So my plan is roughly the following. Chapter 2 was going to be a discussion in more detail of what the Poincare group is, and also how it gets extended to the conformal symmetry group. So this is one I'm a little bit worried about, because I think probably a lot of you are maybe a little bit more advanced in your education, and you've maybe already seen the Poincare group ad nauseum. So I may try to be a little bit brief with that. But with the conformal symmetry group, I'll try to take my time. And in that, I'll also talk about how when I introduce a defect that will break some of the conformal symmetry, I'll talk about what's left after we introduce the defect. So chapter 3 is going to be constraints of conformal symmetry, in particular on correlation functions. So I'll talk a little bit about the case without defects, which I think you've already seen some of in the lectures with Nikolai this week. But I'll also emphasize the less familiar case of what happens when there are defects. You've got less symmetry, and then you have fewer constraints on these correlation functions. So there's less that's fixed. And in chapter 3, I think we'll also discuss a little bit about Noether's theorem and how it, for some simple conformal field theories, how it leads to the symmetry currents associated with the conformal symmetry group. Okay, so that's chapter 2 and 3. And then chapter 4, I want to talk about what happens to these kinds of theories if you promote them to curved space. So we're going to talk about conformal symmetry in curved space. And this will let us talk about also in a little bit, with a little bit more ease. It will let us talk about 2 important operators One is the stress tensor, and another is something called the displacement operator, which appears in these defect theories. And we'll also introduce a ward identity that will actually ward identities, which will be useful for computing correlation functions with the stress tensor and the displacement operator inserted. We basically find an identity that relates the correlation function without this insertion to a correlation function with the displacement and stress tensor inserted. So that will be chapter 4. Chapter 5, we'll discuss two important tools for dealing with conformal field theory. One is called radial quantization. I got the sense that Nikolai Bobov touched on this a little bit in his lectures, although maybe not in great detail. So I think it'd probably be worthwhile discussing this a little bit more slowly and carefully. And the other is the so-called operator product expansion. And that will lead naturally into a discussion of so-called conformal blocks. And perhaps a more rigorous definition of what a conformal field theory is. Conformal blocks are a nice compact way of encoding the information in correlation functions, and they also give us some deeper insight into what the possible behavior of all these correlation functions are. And if you knew all the correlation functions in a conformal field theory or a quantum field theory, that's, I think, one way of thinking about what the definition is, right? Correlation, in some sense, the correlation functions and spectra of the theory define the theory. And then finally, well, not finally, there's 3 more chapters I have in mind. I have a chapter 6 where we'll discuss the conformal bootstrap. So this morning's lecture, I saw there was a lot of that, and we'll do it a little bit more slowly because my emphasis is on conformal field theory. In particular, we'll talk about unitarity bounds, which I think without which it's really kind of hard to understand what's going on with these constraints that emerge from the conformal bootstrap. And we'll also talk about the role of defects and boundaries in this context, how you might try to understand what a conformal bootstrap constraint is for a theory with a defect or boundary. And then kind of finally, my two payoff chapters, we're going to discuss at length the trace anomaly. So we'll learn that classically anyway, the trace of the stress tensor should be 0. But there's a very interesting and long story about what happens quantum mechanically, where it's not 0. But the way it can be non-zero is very restricted and tells you a lot of information about the kinds of behavior that the conformal field theory exhibits. So it's not 0 quantum mechanically. There's an anomaly. And we're going to do that not just in the case, the vanilla case where there's no boundaries and defects, but we'll talk about the very rich story that emerges when there are these additional structures, these extended objects, these defects in the theory. And then finally, chapter 8, I'd like to talk about 2 examples. There's the phi-4 theory. So this is this Wilson-Fisher fixed point or Icing thing that's in the Icing Model universality class that Professor Bobov talked about in his class, but in his lectures. But of course, there wasn't a boundary in that context, and we'll add a boundary. This is an old story that was worked out in great detail, actually, in the late 70s and early 80s, but it may not be so familiar, and we'll do it from a more modern perspective using bootstrap techniques. And another very nice example is mixed dimensional quantum electrodynamics. This is a case where you have a gauge field in the bulk, a photon in the bulk, a 4-dimensional photon, and it's allowed to interact with charged matter on some defect. And we'll see what kinds of behavior emerge from that interesting coupling where, say, you have a plane with some electrons that are constrained to it, like graphene, and a 4D photon, which conveys the interactions between the electrons. What kinds of correlation functions can we compute? What can we learn from the constraints of conformal symmetry in this context? So I view these last two chapters, and I hope we'll have lots of time for them since I have so much time, at least it feels that way at this point, to discuss them next week when I'm there in person. Are there questions about the plan? And I should emphasize when I'm going through this outline, I originally taught this course here at KCL, and it was a rather different course and a slightly different audience. So the original course had no boundaries and defects. And so what I was originally going to kind of go through that course really quickly at the beginning to bring you up to speed on conformal field theory, knowing that you're probably slightly more advanced stage of your education than the students I was teaching here at KCL. And then introduce defects and boundaries. But as I was preparing these lectures, I found, at the end of every chapter, I could add 4 or 5 pages just about what happens with defects and boundaries. And so I decided to kind of intersperse it, to grow this series of lectures based on what I taught last year, just using, without defects or boundaries. That's kind of my plan. So are there questions about the outline? Well, I hope you're all excited to learn about this and excited as I am about these kinds of things. And so I've tried to show you why I think it's important, and I hope I've convinced you. But before we get started, I wanted to take some time to tell you about dimensional analysis. And to start with a problem that looks like it has absolutely nothing to do with what I'm going to tell you afterwards, but I think does at some fundamental level. It's about a way of thinking. So dimensional analysis. And I think about this as a way of solving problems we might otherwise have no clue where to begin. It's a very powerful technique, and it can be used far outside of theoretical physics. And they tried to emphasize this to me as a graduate student a long time ago at Princeton. I'm not sure I really appreciated it as much as I should. And one of the ways they tried to emphasize it is they would ask these kinds of questions on the general exam at Princeton, which I think no longer exists, or at least not in the same form as it used to. So here's a famous question. It was actually phrased in a slightly different way, as in terms of how fast a bug that glides on the surface of the water, how fast it can travel. But let's phrase it in a slightly simpler way. This is the speed of capillary waves. And I emphasize they didn't ask this question because they expected us to know anything about the physics of capillary waves or hydrodynamics. They asked us this because they wanted us to be able to think about problems in a certain way. So what is a capillary wave, right? It's you're standing on the side of a pond and you throw it into the pond, and it produces these circular ripples that travel out. And we want to figure out roughly how fast those waves trickle out. And let's say the problem goes and it tells you the surface tension as a kind of hint about where to begin. It says that the surface tension of the water, let's call it sigma, is 72.8 millinewtons per meter, which I believe if I change into something slightly more pedestrian is, well, let's not write it quite this way. Let's just say it's the same as same units, well, up to some rescaling as kilograms per second squared. So it's a force per unit length. We could convert it into kilograms per second squared. So we sit down and we think, and I've not, no, okay, I don't know, maybe I don't know Navier-Stokes, I don't want to derive it, but it's asking me for a speed, which I know has units of meters per second. And maybe some other things that should go into this are the density of water, rho, which has units of kilograms per meter cubed. And maybe another thing that should go into it is the acceleration due to gravity, g, which I know has units of meters per second squared. So maybe the answer should involve those three quantities. It doesn't seem like physically reasonable for it to involve anything else. And then I think, oh, well, I basically have three equations and three unknowns here, right? I'm supposed to combine rho with some coefficient, sigma with some coefficient, and g with some coefficient, and it's supposed to give me a velocity, which I'm able to measure in meters per second. And so I basically get three linear equations that I learned that a plus b, if I look at the way the kilograms to add up, so I've got 1 kilogram in density and 1 kilogram in the surface tension, so a plus b had better be 0. That's from kilograms. I learned that the seconds had better, the meters had better sum to 0, so I've got minus 3a from density. And then I have, what else do I have? I've got plus c equals 0 from acceleration due to gravity. And this had better sum to what? It better sum to 1. This is the constraint on meters. And then finally, for seconds, let's see. So I have minus 2b from the surface tension plus, no, it's going to be minus again, minus 2c equals minus 1 from the seconds, right? So I ought to be able to find an exact solution. We can do that in probably real time here. Let's just copy this onto the next page. And try to solve it. And I guess we should remember, how did we associate this? So A was associated with the density, B was associated with the surface tension, and C was associated with gravity. So I go ahead and I solve this. Let's see what I can do. So I take these two equations and I learn that minus 6a minus 2b, just take twice the first one, add the second one. This should be 1 if I've done my arithmetic correctly. And then I take that guy into this and I combine it and I learn that minus 6 plus 2a is 1. And so I learn that a is minus a quarter and that b must be plus a quarter and that c must be plus a quarter. And so my estimate for the speed then should be something like sigma to the quarter, g to the quarter over rho to the quarter. And that's was supposed to be the right answer from the point of view of this generals exam at Princeton long ago. And it's sort of to demonstrate the power of dimensional analysis in solving problems that you might otherwise have absolutely no idea where to start. And indeed, this gives you a pretty good answer. If you plug in this, what is it, 72.8 millinewtons per meter that I wrote down earlier, and I assume you know the acceleration due to gravity and the density of water. You got to be careful to put everything in kilograms, meters, and seconds. I believe what you get out, if I did my math right a while back, is 16 centimeters per second, which seems kind of reasonable if you've ever been to a pond and thrown stones in, that those waves travel at a few centimeters per second. And so you could also turn this around and use this as a way of estimating the surface tension of water. And if you're serious about this, you can then go and open a textbook on capillary waves and figure out exactly where this formula might come from. And as it turns out, it's a bit more sophisticated than this, but as a back of the envelope calculation, I think this is kind of a superb example of the power of this method. So what happens in our field? What's the kind of analog setup in high energy physics? So famously in our relativistic context, we always set the Planck's constant and the speed of light equal to 1, which makes us work in a very funny set of units. At least it was funny when I first saw it. I guess at this point it seems very natural. We're just left with one-dimensional quantity. And you should take this fact very seriously. And I think, again, I don't think I appreciated this enough as a young student. The power of this observation. You can always keep coming back to this to really check your results and make sure things make sense, and also to develop your insight, intuition for how different field theory should behave. So there's only one thing, there's mass, which is the same as 1/length in this funny system of units. And let's look at an example and see what we can learn from just dimensional analysis considerations. So this is going to be an example of a free scalar field in d dimensions. So it has a kinetic term. Let's assume it's a real scalar field, so I don't have to worry about complex conjugation. We'll give it a mass term. And the first observation is that S is dimensionless. Why do I say that? Well, if I have a path integral now, right, there's an integrand in the path integral, which goes as e to the I s. Used to go as e to the I h bar s, but h bar I set to 1. And so now it goes as e to the I s, and so S must be dimensionless. And if I look at this first term in my free field theory, I can conclude then that the field phi itself has a engineering dimension that goes as d/2 minus 1. So that minus 1 is to make up for the derivatives, right? The derivatives look like 1/length, which is the same as mass. So we've got two derivatives, two factors of mass. Those are going to cancel the factors of minus 1 here. The d/2 adds up to give d. Everything is dimensionless as it should be. And the way I'll write that going forward is I'm going to say that phi has a scaling dimension, which is d-2/2 for free field. And from this, you'll also see that m, which is a mass, has dimensions of mass as it should. It's weighted the same way as the derivative operator, which is 1/length. 1/length is mass. So everything seems consistent. Okay. Next step. We ask, what happens with an interaction? We add g phi to the n. And we'd like to try to keep g small. We'd like to try to do some kind of perturbation theory. But we notice immediately that g can't be dimensionless. And so you can't really talk about g being small or large on its own. We have to talk about it being small or large compared to something else with the same dimension. So we have to ask, small compared to what? Well, what we can do is we can introduce a dimensionless quantity. We'll call it lambda. We take g, we divide by some energy scale, which is the same as a mass scale, which is the same as a 1/length scale. And to make it dimensionless, well, I had the d from the integrand, the d dx, and then I've got these n factors of the dimension of the scalar field. That has to be how g scales in order for the action to be dimensionless. So this should be a dimensionless ratio. So I can talk about this being dimensionless. And what is this E I've introduced? Well, I have in mind that I'm doing some kind of physical calculation, like I'm scattering these particles, and I want to know, what the interaction is at the energy scale of the particles I'm using to do the scattering experiment. Or I have some temperature I'm interested in, which is maybe of order this energy. So I'm looking at the field theory at some temperature. Anyway, this is a dimensionless quantity. And so I have this characteristic energy scale. And in perturbation theory, I would imagine that I can get some kind of result from this, which would be a sum, a Taylor series expansion, right? J equals 0 to infinity, some coefficients Cj, which may in principle be very difficult to compute. But order by order, I should get sort of higher and higher contributions in this dimensionless parameter lambda. And maybe, hopefully, if lambda is small, I can just stop at leading order or so. And we learned from this that the sign of this exponent is going to be critically important to determine, how the perturbation theory behaves. So let's just copy this and go on to the next page since I've run out of room. I really need to get a larger iPad, I think. Let's see, copy. Put it there. And I want to say that the sign of d minus n delta phi is super, super important. So let's consider the case where it is positive. What does this mean? It means that lambda is small when E is large. So for high energy processes, I can think of this as some perturbative effect on the system. However, lambda gets very large when E is small. So I can no longer trust perturbation theory if the energy gets low enough. We talk about such a case as being relevant, such an interaction as being a relevant interaction. It's important or relevant at low energy. We also have the case d minus n delta phi is less than 0. This implies that lambda is large for large energy. So now in this case, if n is big enough, I can't trust this term when the energy gets too large. It becomes more and more important at large energy. And lambda is small for small e. We call such a case irrelevant. It's irrelevant at low energy. So the emphasis here seems to be on the low energy limit. I guess this is a nomenclature that came from the condensed matter community. And so the emphasis there was on what systems do in their low energy or low temperature limit. You'll see similar nomenclature in the quantum field theory class. I'm sure you've probably already seen it. Maybe I'm telling you a lot of stuff you know already. So in the field theory, quantum field theory or traditional particle physics community, relevant becomes, what does relevant become? It becomes normalizable, and irrelevant becomes non-normalizable because they care more about what happens at high energy, and it becomes, you can't deal with it at high energy, you can't normalize it at high energy, and it's a problem. So there's a sort of flip in the emphasis there. And the case that we care most about in this course is the case where this guy is almost 0. So in the case where it's 0, we call this classically marginal. And the reason I'm calling it classically marginal is it often turns out that when you look a little bit more carefully and you do some loop corrections, you'll find that even in this classically marginal case, that delta phi will no longer be exactly its free field value. It won't be this d minus 2 over 2. And then once it's no longer d minus 2 over 2, this condition d minus n delta phi will no longer be 0, and so it will be slightly irrelevant or slightly relevant as a result of the loop corrections. But if it were true that delta phi was still d minus 2 over 2, we'd have scale invariance. We'd have a theory whose rules don't depend on the energy scale. And that scaling symmetry is an important generator for the conformal symmetry group. And so we would have come closer to the topic of the lectures today, closer to conformal field theory. Okay. So that's the lesson. And I have a bunch of nice examples that I'd like to point out to you. And I guess we have about 20 minutes left. And so I think I'm not going to do all of the examples, but we'll work out a few of them as we go on to try to sketch out the landscape of conformal field theories using these kinds of considerations. Are there questions before I go on? Okay. No problem. So we have this action. -1/2 d dx d phi squared plus, well, let's get rid of the mass term. Let's assume it's massless, because the mass term would have mass dimension, of course, make the physics depend on scale. So mass term, if I had a mass term in this theory, it would not be conformal. So let's just fix this to be our action. And the question I'd like to ask to start out with is, for what pairs of n and d do I find a classically marginal interaction? Does d minus n delta phi equals 0? And it's interesting how this condition will kind of zoom in on very special field theories that people have spent a lot of time thinking about, maybe for exactly this kind of reason. So I guess at this point, I really wish I was there, because I could maybe try to get you a little bit more involved in helping me work these out. So I guess I guess I need to make a decision about which ones to work out and which ones not to work out. So let's work this one out, since I think we have plenty of time. So what was the condition? So it's d minus n d minus 2/2. I want this to be 0. Now I'll just point out, let's look at the case d equals 4 to start out with. In this case, d minus 2/2 is equal to 1. The dimension of a free scalar field in 4 dimensions is 1, useful number to remember. And so I need to know for what n is 4 minus n equal to 0. And clearly that's when n equals 4. So we see that a g phi to the 4th interaction is classically marginal. And this lands us right on the example that was, I think, a prominent character in the talks earlier this week, right? This is this Wilson-Fisher, this is model that flows to a Wilson-Fisher fixed point. It's also sometimes called the ON model if you make phi a vector field and give it more than one component. It flows to in the case, the simple case where phi is just a real field, it flows to this Icing Model universality class. So it's a very interesting and important example that somehow we've landed on right on the nose just through these dimensional analysis considerations. Why don't we look at d equals 3? So in this case, d minus 2/2 is 1/2. I think this also showed up in the lectures this week. And so now I need to know when 3 minus n/2 is 0. That's a little bit harder, but I think I can still do it. It's when n equals 6. So in this case, in 3 dimensions, I should look at a g phi to the 6th type model. And this winds up being related to something called the tricritical Icing model. And it's again a field theory that has seen an enormous amount of attention starting in probably the 60s, although the papers I was reading when I wrote a paper about it myself were often in the early 80s or late 70s. So again, these simple considerations are landing us on a famous example of a field theory in 3 dimensions. G5 to 6, the tricritical icing, something in the same universality class of tricritical icing. And I'll let you work out on your own if there are any more examples in the system which are classically marginal. Are there questions about that? Maybe I should pause for questions. I really kind of want a little bit more interaction at this stage if I'm going to be working out problems in my notes. No questions? Okay. Let's do a different problem. This one I won't work out for you. I'll let you think about it on your own. Let's think about fermions. S equals integral d dx I over 2 psi bar d slash psi. And let's introduce an interaction of the form g psi bar psi to the n. So I'll ask again, what pairs dn yield a classically marginal interaction G. So this time there's a little bit more work to do. You've got to find out first the scaling dimension of the fermion. And I believe, well, let's do it. So here what's the condition? That delta psi should be d minus 1 over 2. This is another important scaling dimension. So let's write it down. And we see now that that minus a half is going to cancel the derivative. And so we get d minus 1 over 2 times 2 is d minus 1 plus the 1 is d. And so the whole action is again dimensionless. And now I'll just point out one interesting example. When d is equal to 2, then delta psi is equal to a half. And so I'm interested in the case where d minus n delta psi, actually it's going to be 2n delta psi, right, is 0. So this is what? This would be 2 minus 2n times a half. Equals 0. And I learned then that n is equal to 2. So there's a classical interaction here which looks roughly like psi bar psi in 2 dimensions. And this is again a famous field theory that people have studied. I think this is often called the Turing model for a 2D fermion. So there were some other parts to this problem in my notes, which I'll just emphasize. You can talk then about, what happens when, this is part B of the problem. You can ask if I add, say, an interaction between a scalar and a fermion, or phi squared and psi bar psi. You can ask, when are these classically marginal? In what dimension? And I'll let you work those out as well. So this example, I believe, has a name as well. This is called the Yukawa theory. All right, so that I'll let you do on your own. So one more problem, actually 2 more problems. Let's think about gauge fields. So we could introduce maybe a Maxwell field, but it could be non-abelian too. It doesn't really matter. Say it's Maxwell to keep things simpler here. And we're going to couple Maxwell to charged fermions. So we have the following kind of action. And you see there's an interaction here between the fermions and the gauge field, and I would ask, what is the scaling dimension of G? And I also ask you, what is special about d equals 4. This is another extremely important example here, and I'm not going to work this one out for you, so but I encourage you to do it yourself. This was, yeah, I think appreciated by me only late in my PhD education. So appreciate it now if you don't already know the answer. And then the final one I'd like to work out for you is connected with these defect and boundary cases. So let's write down the following action. S equals minus a half integral d dx. So we're going to have a massless scalar field in d dimensions. And in the spirit of boundaries and defects, I'm going to introduce a planar defect in p dimensions with this kind of coupling again, g phi n, and it will be localized on the plane. So this is my planar defect. I'm not specifying the codimension. And now you can play the same game. And this game, I'm pretty sure you probably haven't played before. But it's very similar in spirit. You can find triples now of the bulk dimension, the defect dimension, and the order of the interaction n, for which G is classically marginal. So again, the idea here is not that it's going to land you on a conformal field theory on the nose. There's going to be some RG flow typically, but maybe you can set things up so you don't have to flow very far, and you still have perturbative control on the conformal field theory that you land on after you do the RG. So you set up with something that's classically marginal, it flows a little ways, ends on something that really is a CFT, but it hasn't flown far enough that you've lost control, theoretical control over how to compute scattering cross sections, correlation functions, etc. So let's think about this one a little bit. I'm not going to work it out for you exactly, but I'll point out a few nice examples. So one is when P is equal to d minus 2, when you have a codimension 2 setup. So there's two normal directions to your defect. So in this case, the condition for marginality, it's not d minus n delta phi anymore, it's p minus n delta phi. This is what has to be 0. So in this case, this is d minus 2 from the p minus n, and then delta phi is still what it used to be, d minus 2 over 2. And so you see very clearly in this case that when n equals 2, when you have a boundary mass term, in this codimension 2 case, it winds up being classically marginal. And in this case, it's actually exactly marginal. It's a quadratic theory. There's no interaction. So there's actually no way for it to flow. So let me just write that down. And this case here where I have an integral, what is it, d minus 2x g phi squared delta of 2 of x, localize on that codimension 2y or whatever it is. This winds up being quite an important example in the study of entanglement entropy. You wanted to compute the entanglement entropy of a free scalar field using something called the replica trick. You wind up having to add this term, or at least to understand the presence or absence of this term in the action. Let's do one more example here, and I'll let you work out the full case on your own. Let's think about the case where the codimension is 1. So P is d minus 2. So this is case 2. So let's see, what do I have in this case? I've got P minus n delta phi is supposed to be 0. This is d minus 1 minus n d minus 2 over 2. So in this case, the different dimensions are going to work out a little bit differently. So we could look at them maybe case by case. Let's look at, say, d equals 4. So now I have 3 minus n is 0. So I've got n equals 3. So there's going to be some boundary interaction which looks like g phi cubed, which at least will be classically marginal. Or I could look at d equals 3. In this case, I've got 2 minus n, and then the scaling dimension is now a half. That's supposed to be 0. So I learned that n equals 4. And so there'll be some boundary interaction of the form g phi to the 4th. So you've just come from a long series of lectures about supersymmetry, and I understand that you learned something about an object called the superpotential. Let's call it W. And that if you have a superpotential, you can compute from it a potential by roughly taking a derivative and squaring it, dw d phi squared. So let me just point out something to you that I already don't understand about these defect and boundary theories, and maybe one of you can explain it to me. I'll point out a very curious looking coincidence, which is if I think about these pieces that have showed up as G times a superpotential, then in the 4D case, I'm going to find a bulk potential, which would look like G phi 4, because d phi cubed d phi is phi squared. I square that, I get phi to the 4th. And in that case, I'm going to get a G phi to the 6th. And those were exactly the cases I talked about before in the original case. Remember, we were looking at what the special pairs were where there was no defect or boundary. And we just went through and we talked about how we got a G phi to the 4th term in 4D as the potential, as a classically marginal potential, and G phi to the 6th in 3D. And somehow, just these finger counting exercises are landing us naturally on this idea that the natural boundary potential, if I'm going to add one, should be related to the bulk potential via some superpotential, even though I haven't introduced supersymmetry at all. So I don't really know what this is about. I can mumble some words about how if I introduce a boundary and I have supersymmetry, it can be very natural to have this kind of superpotential boundary term in the action so that I don't break too much supersymmetry through having added the boundary. But already these kinds of very elementary considerations, I think, have landed us on an interesting observation, which probably would lead somewhere, but I don't know what the end story is here. All right, with that, I think I have 3 minutes to spare, but I think I'll end just a little bit early, and I'm happy to entertain questions.
Hi, can you please repeat once again after introducing superpotential?
Can I repeat what I was saying?
Yes.
I'm just pointing out, let's write it all down again. So I'm thinking about having the following action, ddx d phi squared plus gv in the bulk plus integral d minus 1x gw. That this is the structure that seems to be emerging from this dimensional analysis computation in d equals 3, where I found...
Hi, can you please change your color? I cannot see
sure.
Actually. Yeah.
I think so, maybe. Let's see. I just do it like this. Color. Great. So in this case, I think I found, what did I find? I found that W, got to change my color. W was phi to the 4, and then d equals 6. I found that W was phi cubed, and that V was dW. D phi squared was phi to the 6th, and in this case, B was phi to the 4. So I think it's just sort of peculiar that these kinds of elementary dimensional analysis considerations are landing us on some structures that should be familiar from your lectures last week for reasons that I don't completely understand.
Okay, thank you.
I have a sort of a question, perhaps. Can you go back a few pages?
Sure. How many pages? I'm not sure how far I should go back. Can you give me some hint about what? Have I lost the audio? I'm not hearing anything. I'm sorry. I know, but I'm not hearing you. I thought there was a question that asked me to go back a few pages, but since then I haven't heard anything.
Oh, hi, sorry, my Zoom crashed.
Okay.
Yeah, you introduced the defect, the example with the phi to the n delta q.
Yes.
Yeah.
Here. Yes.
Yeah. What do you exactly? What does this interaction? What does this term exactly mean? I don't think I fully understand.
You're saying that these fields have an interaction which is localized on the boundary, so they can. If you do it from a quantum field theory point of view, if you have these Feynman diagrams, the interaction vertex has to be on the defect.
Oh, I see. This seems a little unnatural. I don't know.
Well, let me give you an example. If we think about graphene, we have electrons that are confined to a sheet of material. They're charged, and we know that those charge interactions are mediated by the photon. But there's no reason for the photon to be on the sheet as well. In fact, we know the photon is a four-dimensional object. And so in that case, it's very natural to have an interaction which is localized.
Okay, thank you. That makes sense.
All right, so I'm done, and next week we'll come back and we'll dive into more technical aspects. But I just wanted to emphasize, I think this dimensional analysis stuff is really kind of deep and important. And I wasted some time with this surface tension analogy just to kind of emphasize that. So it may in fact be the most important thing I say all week. So maybe you've seen it before, but I'd like to kind of hammer that point that there's a lot of very useful physics just by counting on your fingers and thinking about how things scale with length and mass and so forth. And I encourage you to work out these examples in a little bit more detail than I did today. It's kind of fun, and come up with your own. Especially with this defect and boundary stuff, I think you're very likely to come up with the field theory that people have not looked at in that much detail yet.
Okay, thank you very much, Chris. Is there any more questions? You're welcome to ask after. We will leave the Zoom room open. So if you have questions after the lecture, please feel free, okay, with this microphone. Okay, thank you very much.